Hello APC Mechanics students, in Unit 2, Newton's Laws of Motion, Class 5, Newton's Second Law, Part 2, then Section 1, Coefficient of Static Friction, Ramp. An object is placed on a rough ramp inclined by theta is at the verge of motion, at the edge of motion. Then here the moment the ramp is rough, it means that we have friction. So we suppose that the box is not moving, so we're talking about static friction, and in the case of the verge of motion or at the edge of motion, we can use the relation that friction is given by the coefficient multiplied by the normal push. The aim of this section is to derive an expression for the coefficient of static friction μs in terms of theta, which is the angle of inclination. And for sure this can be done using Newton's second law. It's a big law. Now, in order to deal with the Newton's second law, we need to utilize the forces that are acting on the box or the object, and this can be done by doing an FVD in which the x-axis is considered the ramp and the y-axis is perpendicular to the ramp. Now, the pull of gravity is down, the normal push is up left, and the static friction is opposite to the tendency of motion. Tendency of motion is down, so friction is up the ramp. And now we're gonna apply Newton's second law of motion given by F net is ma, where F net is the total forces acting on the object, m is the mass of the block, and a is acceleration. Now vectorially it's given by, and let's decompose this vector equation along the x-axis. And the angle between the pull of gravity and the y-axis would be theta, which is the angle of inclination. So along the x-axis, what do we have? We have the pull of gravity. Then here the y component would be given by fg cosine theta, and the x component is given by fg sine theta. So that would be fg sine theta. The normal push is 0 and the friction is minus ff in the opposite direction, and the acceleration in this case is given by 0 because it is at rest, it is at the verge of motion. But we know that friction is given by the coefficient multiplied by the normal push. Then this expression can be replaced here, and let me repeat again why we are allowed to use this expression: because we are at the verge of motion. So now in this case we are searching for the coefficient μs. However, we have two unknowns, μs and fn. Now fn can be determined by considering the y direction, and we know that in this case the normal push would be balanced by the pull of gravity multiplied by cosine theta. Now replacing this here, we would get fg sine theta minus mu fg cosine theta, and we're still interested in determining μs. Now taking this to the other side, we would get, and we can cancel the pull of gravity on both sides, and we're left with the μs to be the ratio between sine and cosine of the same angle, which is tangent theta. Then the coefficient of static friction for an object on a rough ramp at the edge of motion is given by μs tangent theta. The important thing is that the ramp should be rough. We are at the verge of motion, then the coefficient for static friction is given by tangent theta. Now section 2, coefficient of kinetic friction ramp. An object is sliding down on a rough ramp inclined by theta at a constant velocity given by acceleration is 0. The moment the ramp is rough, it means that we're dealing with friction because we have motion which is sliding down, then this is kinetic friction. The aim of this section is to derive an expression for the coefficient of kinetic friction μk in terms of theta, angle of inclination, and this can be done using Newton's second law. But first we need to utilize the forces acting on the body. Pull of gravity is down, normal push is up left, and the friction is opposite. So here this should be kinetic friction. Now let's apply Newton's second law. F net is ma. The total forces are given by the pull of gravity Fn and Ff, which is ma. Now along the x-axis, the pull of gravity can be replaced by fg sine theta. Ff would be in the negative direction, and the acceleration is 0, although we have motion, but it's constant velocity. Now we know that this can be used always and forever independent of the type of motion, and this would be replaced here. And now we're left with two unknowns, μk and fn, but remember that we're interested in determining μk. Fn can be determined by considering the y direction, knowing that fn is balanced by fg cosine theta, replacing in the previous equation, taking to the other side, simplifying with the pull of gravity, we're left that μk is given by the ratio of sine over cosine and tangent theta, which means then the coefficient of kinetic friction for an object sliding on a rough ramp at a constant velocity is given by mu k, which is tangent theta. Now it's healthy to refer to the previous summary and completed. Then therefore section 3 summary, we can complete the table that have been introduced previously. So for an accelerating body, we refer to two different columns given by the dynamical system and the expression of the acceleration. For a free falling body with no resistance, the acceleration will be given by the gravitational field strength G. If the body is sliding on a frictionless ramp, then G would be modified into G sine theta. If now the ramp is rough, the modification to G sine theta is that we're gonna add minus mu k cosine theta. Why mu k? Because we have motion. Now for a non-accelerating body, so the first table is for accelerating body, the second table is for non-accelerating body. Now what are the dynamical systems that we're talking about? We're talking about an object placed on a rough ramp, and we're at the case of the verge of motion, edge of motion. Then the coefficient of static friction is given by tangent theta. Here no need to talk about the acceleration because we know that the acceleration is 0, the box is not moving. And if the object is placed on a rough ramp sliding down at a constant velocity, acceleration is 0. Also we have that mu k is tangent theta. Now section 4, boxes on a level surface. 3 blocks of different masses MA, MB and MC are placed on a frictionless level surface. So we have 3 blocks MA, MB and MC that are in contact and placed on a frictionless level surface. Level surface is a horizontal one. The system is pushed by a horizontal constant force F at the mass MA. All of these 3 together are being pushed to the right by constant force F applied to the block MA. The system MA, MB, MC acquires a constant acceleration A. All 3 blocks have the same acceleration Y. First of all, they're gonna accelerate because they are submitted to unbalanced forces, mainly coming from the capital F. And they will have the same acceleration because we're assuming that all 3 blocks along the motion will remain in contact. The aim of this section is to study the forces of interaction between the blocks. Let me explain more. Now here different systems can be considered at this level. We can consider MA as a system, we can consider MB as a system, and MC as a system, and MA, MB and MC combined. Now if you consider MA alone, now what would be the forces acting on MA? We have the pull of gravity, we have the normal push, we have the force F pushing to the right, and we have the force of interaction between MA and MB, which is pushing toward the left. Because MA sees the block MB to be a support, and MB will exert a force on MA similar to the normal push, to the characteristics of the normal push, but in this case we name this force to be the force FB exerted on A. Now however, if we consider the block MB, what are the forces acting on the block MB? So we have the pull of gravity, which is down, we have the normal push, which is up. Now the block MB cannot see the force F, so we cannot say that the capital F is being applied on MB. However, MB is being acted by 2 forces from blocks MA and MC. So similar to the argumentation that we have done for MA, or the force of interaction between A and B, so there will be a force exerted from A on B, which is to the right. So that would be FA on B, because mainly MA will be exerting a force on MB, pushing it to the right. Similarly, block C will be exerting on block B a force FC on B to the left. And notice that because block B will be moving to the right, I have represented vectorially FAB to be greater than FCB. Now if you consider the block C, what are the forces acting on the block C? We have the pull of gravity, which is down, coming from the mass of MC. We have the normal push, which is up. I have represent them to be balanced forces. There is no motion up or down. And there will be only one force acting from B on C, which causes the block C to move to the right, and that would be FBC. So for this reason, The aim of this section is to study the forces of interaction between the blocks, but first let's determine the acceleration A of the system. So whenever we're dealing with such configurations, the first thing that you should do is to determine the acceleration of the system, and this can be done using Newton's second law. And now our choice of the system would be as a whole, including MA, MB, and MC. So what are the forces acting on such system having a mass MA plus MB plus MC? That would be the pull of gravity down, the normal push which is up, and the pushing force F to the right. And now we can apply F net is MA. F net would be the total forces acting on the system given by this, and that would be the pull of gravity plus the normal push plus capital F, and the mass would be replaced by the total mass of the system given by MA plus MB plus MC. Now this is a vector equation. We need to deal with it solely along the horizontal and or the vertical. Along the horizontal, that would be the pull of gravity is 0, the normal push is 0, and capital F is to the right. So the acceleration is A and the masses remain the same. So the acceleration would be given by capital F divided by MA plus MB plus MC. Then the blocks accelerate equally by capital F divided by MA plus MB plus MC. Now let me repeat and say, whenever we have such type of configurations, the first thing is to utilize that the acceleration is given by capital F divided by the total mass. And similarly, the pushing force, if you isolate for F, is given by the total mass multiplied by the acceleration. Then the blocks accelerate equally by an amount of acceleration given by that, and the pushing force is also given by the total mass multiplied by the acceleration. Now we're interested in determining the force of interaction between the blocks A and B given by FAB, which is equal to FBA, and they are equal due to the Newton's third law, as we shall see later. Now what is the force FA on B? It is the force exerted by A on B, is to the right, that would be FAB, and FBA would be the force exerted by B on A, to the left. So whether we determine FBA or FAB, that would be perfectly the same. The direction would be exactly opposite, but we can determine one of them and the other would be directly deduced. Then we can either consider block A or B, but here our choice should be wise in a sense that it is easier to consider A since it is on the edge. Now the forces acting on MA are given by what? This is the FBD of the block A. We have the pull of gravity, which is FGA. We have the normal push FNA. We have the pushing force to the right, and we have the force exerted by B on A. Sorry, F to the right and FB on A to the left. Then now we can apply Newton's second law given by F net is MA. What are the forces acting on the block A? Here we're only considering not the forces acting on the system, but on the block A. We have FGA, FNA, capital F, FBA, and MA multiplied by A. Notice that here the mass has been only replaced by the mass of A since we're dealing only with the block MA. And now we're gonna project this equation along the horizontal. That would be 0, 0 plus capital F minus FBA is MAA, considering the fact that the right direction is the positive direction. Now we're interested in determining this force, FBA, which is the force of interaction between block B and A. Capital F, we know now, it's given by the total mass multiplied by the acceleration, have been determined here. So in this case, we're searching for FBA. This can be taken to the right and this taken to the left. Now this would cancel with this. So we can factor out A, then FBA is given by MB plus MC multiplied by A, and we know that the acceleration is given by capital F divided by the total mass. And finally, the force FBA is given by the following expression, which is very important. It is the capital F multiplied by a factor. This is the factor, which is a ratio between the masses MB plus MC divided by MA plus MB plus MC. So the force exerted by block B and A, or by block A on B, is given by FBA, which is the masses MB plus MC divided by the total mass multiplied by the force F. Now we're interested in determining the force of interaction between blocks B and C. Then we can either consider block B or C. Why we can consider either of the blocks? Because block B exerts on C a force given by FBC, and block C exerts on block B a force given by FCB. Whether we determine this or that, they are perfectly the same. and each of these forces appear whether we consider block B or C, but since C is on the edge, it's easier to consider C as our system. Then let's consider block MC. Now what are the forces acting on MC? We have the pull of gravity down, the normal push up, and the force exerted by B on C to the right. Now we can apply Newton's second law given by F net is ma. We have pull of gravity plus the normal push plus Fb on C is equal to mca. Now we can project along the horizontal, and notice that the mass has been replaced by mc. Since we're applying this law solely to mc, 0 plus 0 plus fbc is mca. We're interested in searching for fbc, and we know that the expression of the acceleration is given by the total force divided by the total mass. So in this case, also the force of interaction can be written as the force F multiplied by a ratio, which is a ratio of masses given by mc divided by the total mass. Now as a summary, we can say that the three blocks A, B and C acquire the same acceleration given by, or equally given by, capital F divided by the total mass. The pushing force can be expressed as the total mass multiplied by the acceleration. Now what different FPDs we can consider? We can consider the system as a whole. We can consider the mass MA, MB or MC solely. If we consider the system as a whole, we have the pull of gravity down, we have the normal pushes up, and the force F to the right. Now if you consider the object A to be our system, so that would be the capital force F acting to the right. We have the force of interaction Fp on A to the, so F is to the right, Fp on A is to the left. The pull of gravity on A down, the normal push on A is up. Now if you consider block B doesn't communicate with the capital force F. However, it communicates with two forces: the force exerted by A on B to the right, the force exerted by C on B to the left, and we have the normal push and the pull of gravity. If you consider the block C, we have three forces. For sure, the block C doesn't communicate with the capital force. We have FBC to the right, we have the pull of gravity down, and the normal push up. Now the force of interaction FA on B, so these two forces are equally according to Newton's third law, as we shall see later, and they are given by this expression, a factor multiplied by the total force. In the numerator, it would be the sum of the masses MB and MC, which is the mass excluding our system, which is A, divided by the total mass. And for the force of interaction, BC, which is equal to CB according to Newton's third law, so that would be the following expression: the capital F multiplied by a ratio given by MC divided by the total mass. And now let's do the following exercise as an exit ticket for today's video. Three blocks A, B and C of masses 1, 2 and 3 kg respectively are initially at rest on a frictionless surface as indicated in the figure above. What force F has to be applied on block C to accelerate the three blocks at 2 meters per second square? So we have the acceleration of the system, we have the total mass of the system, so F can be directly determined by the total mass, which is 6 multiplied by 2, and that would be 12 newtons. But let me consider the case to do the solution explicitly. Suppose this is a free response. Now we're gonna say, so we need first to do the FPD in order to utilize Newton's second law. So if we're considering the system as a whole, that would be a 6 kg body represented by a dot. You have the pull of gravity down, this should be done by a ruler. We have the normal pushes up, and we have the capital F acting to the left. And now we can apply Newton's second law. So let me write apply Newton's second law given by F net is ma. Now what are the different forces acting on our system combined? That would be the pull of gravity, capital F and capital Fn, which is equal to the total mass given by ma plus mb plus mc multiplied by the acceleration. Now we'll consider the x-axis to project, or the horizontal. So that would be 0 plus capital F. Let me consider the left direction to be the positive direction, plus 0, which is the total mass given by ma plus mb plus mc multiplied by the acceleration a, which is considered to the right. Then capital F would be given by the total mass 1 plus 2 plus 3 multiplied by the acceleration, which is 2, and that would give us 6 multiplied by 2, which is 12 newtons, and the correct answer in this case is E. Then that's it for me in this video guys. See you soon in a new one.